is Gucci, internet dwellers? It's your boy. We will be covering basically the final sort of scenarios, 4 scenarios which they can present to you in your exam. We covered basically pulleys, incline, slopes, and now we're going to be doing what I'm calling the string tension question, and this will cover basically the final sort of scenarios. And then progressing from this, we will introduce, they combine these scenarios and introduce energy and introduce power and stuff like that. So that's why it's actually quite important that you watch these videos from start to finish in the order that I present it in the playlist itself. This is all premeditated, baby. Okay, so we have basically this, we're just going to be going through questions here because you don't really need any extra theory to understand. So we have the connected particles or masses, which is where you have 2 masses or particles connected with a string. You have to use tension in that string and find the tension in the string. We'll do a question on that. You also have the wall mass tensions, where you have a particle or mass connected by strings to some wall. Question on that, and you have all that. And then we have this smooth ring kind of example, which they use sometimes. Extracted those as well, and we'll do a question on that also. Obviously, I've answered them all for you. Took me ages, so hopefully you use that. I think it's a really good resource. But yeah, so all we're going to really do is go through questions here. I would highly recommend to watch, I mean, you should have already, you're in this deep, watch my resolving vectors question. It's very important for this one. And so after this, we would have covered all those scenarios. We've got the forces, resolving vectors, got the forces pulley, got the forces incline slope, and now we've got this forces string tension. And then, as I said, we'll introduce power, more complicated scenarios where they mix and match these pulleys and inclines and stuff. And that'll come in the next few videos. Anyway, let's do some questions. Righty. Okay, so they're giving us this scenario, 2 blocks like this. So I'm going to start redrawing it immediately. Why? Because I want to get it all in general form, and also I want to visualize what's going on. Got this block A, B, connected by the string. I have the weight of A acting down. We know we have this force up. As we know from the incline question, this will be theta? No, it'll be, what are they calling it? It's alpha. It's actually supposed to be used in particles. Oh, WB, the weight of B. This will be alpha. So string, so it's a smooth surface, so we don't have to worry about frictional force. String is inextendable, which is actually quite important, because if it was extendable, then so pull and then back and pull back, and it would be doing all this goofy stuff. But you won't have to worry about that. So okay, so we want to find the acceleration tension. So this is actually quite similar to the pulley question, or all these kind of questions actually that involve like is you have to use Newton's second law to resolve the forces about each mass. So in this case, so let's write out what they're giving us. So F was 6 newtons. WA will be 50 newtons, right? 10 times, oh no. WA will be 40 newtons, 10 times the weight. WB will be 50 newtons. And what else they give us? And then we have that 10 alpha. Our angle is 7/20. And it wants us to find the acceleration and the tension in the string. Now it's important to note that the tension in the string will be acting like this. You have the tension on block B will be acting, sort of pulling it down the slope, which makes sense because pulling it up is going to be pulling it back, opposite direction of the force. And then the tension for the block B will be the same, but it'll be pulling it up, right? Rope is making it move up the slope in the direction of the force. That's really the only difference here. So it's just understanding that. Hopefully that makes sense. I mean, it does make sense if you just visualize it. You know, the tension couldn't be acting down. I mean, it's not going to be pulling it down the slope. Like, anyway, so find the acceleration. So we want to resolve the forces about A and B. And then we'll be able to set up an equation with the acceleration and the tension, both of them, solve them. So for A, we want the sum of the forces for A. This is going to equal to the mass of A from Newton's second law. So A times the acceleration of this block A, and the acceleration will be the same for both, right? Because it's an inextendable string, so the whole system is going to be accelerating. So block A and block B will be accelerating at the same rate. Okay, so therefore, well, what is the sum of these forces acting on A? So on A, we have the tension force acting up and the weight down the slope, and that's it. Tension minus the weight down the slope, which is Wx, so equal to the mass of A times A. Tension, so therefore we can say the tension minus, what is Wx? Well, this is just the opposite over hypotenuse, so we can say this is just WA sine alpha m8. So that's one equation which will be useful. The second equation, FB is to the mass of B, A, so the sum of the force B, but for B we have this force acting up minus the tension acting down the slope, and then minus the weight of B acting down the slope. B. E. Okay, and I guess we could box it up. It's not that important. Number it. So it's 1 and 2, equations 1 and 2. Okay, so now if we actually put some of these values in, I guess, well, what are we trying to find? We're trying to find the acceleration and the tension. So for equation 1, we can say, well, the T equals to A plus W sine alpha. And then if we substitute in 1 to 2, so I'm keeping it in general form for now, and I'll substitute the numbers in later. F minus T, which is this, minus now we have an equation for A, and we actually have all these values. So in fact, just quickly here, sine alpha, shift tan of 7 over 24. You know, this is some 16.26, like a huge number, rational number is alpha, but 0.28 for that. So if you put this into your calculator, find alpha, and then replug that exact number in, you get sine alpha equal to 7 over 24. Useful. Let's plug these numbers in here. The F, which is 36 minus the mass of A is 4 minus 4A, A we don't know, plus WA is 40 times sine alpha, which we just found, which is 7 over 24. Minus B is 50. 7 over 25 is 2. S of B was okay, so we have a bunch of stuff going on. So 36 minus, simplify this, plus, what is this? 40 times 7 divided by 25. 6 over 5. It's 57 divided by 15. 5A. Or we get 36 minus 4a minus 56 over 5 minus 14. It's 5a. That over, we're going to get 9a equals 2. 36 minus 56 over 5 minus 10, 8. So a equals 2, that divided by 9, which is 1 point. The acceleration of these blocks individually or the system overall is 1.2 meters per second squared, and therefore we want to find the tension, or from 1, the tension will equal to ma, which was 4, times now acceleration, which is 1.2, plus wa, which was 40, sine alpha, which was 7 over 25, which we found before, 7 over 25. Just to make it clear, what I did there to find that is I just found alpha, so it would be the inverse of inverse tan of 7 over 24, and then I plugged that exact number into sine alpha, and you get that fraction. Okay, so therefore the tension, and obviously you could have plugged it into 2 if you wanted to, but this is just a simpler equation. That's why I used it. Tension is equal in both of the masses, so 4 times 1.2 plus 7, 25 newtons. 16 newtons. It's pretty gangster, you know. Imagine having a physics unit named after you. 20 Jacobs. Let's go. Tick. At a particular instant, the speed of the block is 1 meters per second. Find the time after this instant that it takes for the block to travel. Okay, so it's just x. So at some time, we have an initial speed of 1 meters per second. It travels at a displacement of 0.65 meters. Right, so check. Okay, and we have the acceleration. Acceleration is meters per second squared. Well, we know an equation. Wait, what does it want? It wants the time taken. So we have this bad boy, S equals UT. Go watch my kinematic. You should, in fact. It's not a recommendation. It's a demand. Watch it. S equals, so now we just plug these in and we can find T. So S is 0.65 equals 1 T plus a half 1.2 T squared. So we get 0.6 T squared plus T minus 0.65. 0. Well, they're 4, so I'm just going to use the credit formula. Get minus 1 plus or minus the square root of 6 squared 4 6a 2a. Okay. Have I done this right? That's why. Minus b plus or minus the square root of b squared. There we go. See, I just need to take my time, you know. B squared minus 4ac. And the reason I knew that that was going to be wrong is because I got some crazy number in here. Usually when you do this, usually it will come out as a whole number. Not always, so maybe don't. Just done so many of these questions. Know when it's wrong. Okay, so this is minus 1 plus or minus 1.6 over 6. Okay, well, it's not going to be the negative 1 because time can't be negative. It could. Our lives probably would be a lot more complicated because then we could go back in time. Yeah, but I don't know how to do that. So I'd like to, but just don't know how to go back in time, I'm afraid. And so t is equal to seconds. That's your answer. Like 0.5 seconds. Tick. Okay, so the important thing you need to understand here is this tension acting inwards for these connected particles or masses. And other than that, it's pretty similar to what we've been doing so far with stuff. Okay, this, so it's important, I'll reiterate again, you should watch the resolving vectors question. It's a lot easier. Okay, so I'm going to redraw this. So, you know, we have this diagram. This is basically just going to explain this diagram. And it's an equilibrium, which means, so the resultant force will be 0. Let's redraw it. It'll stay consistent, even if my drawings are horrendous. This is all this theta 1 and theta 2. Weight will be acting down, so the weight. What else do we need? This is, we'll call this T1 and T2. So, okay, so let's write out what they have. Theta 1 was 45 degrees. Theta 2 was 60 degrees. T1 is T. T2 is me. W is going to be, well, M times 10. So I guess. Okay, so find T and M. Well, it's at equilibrium, so as it's at equilibrium, the resultant force of this entire system, X component and the Y component of this resultant force of the entire system will be. Okay, so what are all the X component? This is basically what we did in our resolving vectors question, but this one involves tension, so I thought I'd do it. So f of x will equal to the X component of this T1, the X component of this T2. That's it, right? There's no other X components because W acts straight down. T1 is going to be the X component of this is, you know, this part here. So we say that the right is positive, so this will be T2. This component of our force, the X component of our force, which is going to be opposite adjacent. So this here, get cos of theta 2 equals opposite, which is this thing that we need. So T2 cos of theta minus opposite adjacent, so same thing, but it's minus because this is acting this way. T1 cos of theta 1. That equals 0. So therefore we get, if we substitute these things in, well, T2 was 20. Cos of theta 2 is 60 degrees. Minus T1 was T. Cos of theta 1 is 5 degrees. 0. Therefore, we get T will equal to 20 cos of 60 degrees over cos of divided by 14.1 newtons. That's your T. And if we want to find the mass, well, that's included in this one. For the forces of Y, which will also equal to 0. We have obviously the T of Y acting up, and the T1 of Y acting up, and the T2 of Y acting up. It's W acting down. So we have T1 sine theta 1. This is this Y component of T, which is going to be opposite hypotenuse. Same concept here. So sine theta 1 is going to equal to Ty over Ty equals T1 theta 1 plus T2 sine theta 2 minus W equals 0. Right, because these act up, the Y component of this T1 and T2 act up, and the W acts down. Okay, so therefore we get, well, T1 is T, which we know is 14.1. Actually quite a long number. It's sometimes important to keep the exact values in calculator, but you don't round too much. You have to be a bit careful with your rounding sometimes. I mean, all the time. Theta 1. This is rounded to 1 dp. Sine of theta 1. 45 degrees plus T2 is 20. Sine of 2 is 45 degrees, and yep, this equals to 10. It's 10 times this, which we're trying to find. So therefore the mass will be all of this divided. Use my answer from the tension times sine of 45. Oh wait, this is theta 1. Oh, this will be 60 degrees. Theta 2 is 60 degrees. Plus 20 sine of 60. .73. 2.73 kilograms. That's your answer. Okay, so that's pretty similar to the resolving vectors question, so make sure you watch that. But these tensions involved. Okay, and finally we'll do one of these smooth ring ones. And actually put this one in deliberately. So actually a little tricky in it. I'm going to teach you a useful trick. All of math is tricks. Space, yeah. You know what I mean? Give the man some space. Okay, so let's redraw this thing. So you can read through it. Let's read through it. A smooth ring of R of mass M, smooth, light and extendable string. So we've got a string now, but it's fed through a ring, which is important because then the tension will be the same on both of them. They're not individual strings. Kind of similar to the coupled masses, the connected masses. The ends of the string are attached to, so basically explaining what we've got here, and it's held at equilibrium, which means the resultant force will be 0. Calculate the tension and in the string and the mass of the string. Okay, let's redraw this string, which is fed through this ring, so it goes like through it. It's a bad line. That'll do. That'll do. That'll do, donkey. Theta 1. Theta, I guess. And then we have a force which acts upon the string. F. Okay, so yeah. This is meant to be at a right angle. String theta. This is at a right angle. It's our ring. Okay, F is equal to 2.5 newtons. Theta is 5 degrees. Calculate the tension. So the tension in the string, because it's one string fed through both of these points, the tension in this part, should they'll both be acting away, right? Because it's pulling it away. It's going to be the same. Whatever it is, it'll be the same because it's all acting the same string. And then we have the ring. So which equals to, does it give us that? No. It's going to equal to the mass, which we don't know. 10 times the mass, we don't know. It's just a little bit before. Okay, so calculate the tension in the string. So what we could do here, which I've been showing you with these proofs, and you could do this, is that you resolve it along the y and x axis, where the y and x axis are acting like this. That means you have to resolve the y component and x component for this A part of the string, the y component, the x component for this B part of the string. The y component will be acting down for W, and the y component and x component for the F part, this F force. You can do that, but there's a lot of work. Instead, what I'm going to do is I'm going to make the axis along this B, R, and RA. So now our axis is, if we kind of look at it like this, up, straight up from R to A will be the y axis. Our x axis will be from B to R. And we can do that because we're just shifting frame and all of the forces will still resolve out to 0. But why are we doing that? Well, because then we have the tension acting straight up here, and the tension acting to the left on the x-axis here, and the force acting to the right on the x-axis here. And so the only actual thing that we have to resolve the y components and x components of will be this W. And so we can actually just come on, drawing. Right, so the y of W will be this part, which will be acting down, opposite to this direction, and the x of W will be acting left. So resultant force, because it's at equilibrium, x Fy, where our x is along this part here, and our y is along this part here. Okay, not up and right and left in the conventional sense. You can do it like that. I'm not saying you can't do it like that. I'm just saying it's easier to do it like this, just to switch your framing. Equals 0. Okay, so our f of x will be, and we're gonna, so we have f of x, so we have the f acting positively minus the tension acting negatively. And see how much easier that was? We don't have to calculate the x and y x components of both of these things. And then we're going to need the x component of this W, which is going to be acting down, left. So equals 0. Get F minus T. What is WX? Well, we're going to need this angle here. Yes, if we think about it, what is this angle here? Well, we have theta, so this angle here will be straight down theta, and what's that 45? Well, this, okay, so this is theta, right? Straight down and then along this A to R, and this is straight down along this A to R, right? So this is theta, and you know, this is acting straight down, so it's going to be, this will also be theta, right? Because this thing is straight, cutting it straight in half. So this is theta and theta, right? I guess you could just put it on the other side if you wanted. This is theta, however way you want to think about it. So the theta here will be opposite, adjacent. I guess I'll just think of it like this. That makes more sense, doesn't it? Let's be honest. Okay, so this theta here. So the W acting WX will be opposite, which is sine theta. Right, so this part here. Okay, so brain, we have this, so we get F 2 point. I'm gonna keep it in general form. So therefore we get, trying to find the mass and the tension. So we get T to F minus W sine theta. F was 2.5. It's 10 m sine of 45 degrees, which equals 2 sine of 45 square root 2. So this is 2.5 minus 10 square root 1 over square root 2. We have an equation for T. Fy, we get acting down, okay, will equal to W. And the only thing acting up is this tension. Tension minus Wy. 0, so we get tension minus W. 0. So we get tension equals to W, which is 10 m, plus theta, which is 40 degrees. And this will also be 1 over square root. So therefore we get T equals to 10 over square root 2 of m. 2. Now we have two equations relating to unknowns. So if we sub 2 into 1, get 10 over square root 2 m equals to 2.5 minus square root 2m. Okay, take that over. We're going to get 20 over square root 2m, 2.5. So therefore m equals to what? 2.5 square root 2 over 10. Which is divided by 20. Equals 0.177. 0.177 kilogram. M equals 77 kgs. Rounded, of course. So therefore T from 2 will equal to 10 over square root 2. And this is the exact form of it, so let's just plug that in. Careful with our rounding. This thing times divided. Because we did it exactly, we get 1.25 exactly. Right, hear that? It's important to be careful about rounding with these things. Chin is 1.25. Okay, so that's that. What was really difficult about that? Okay, well, what I was trying to show here is the switching of frame to make the calculation easier. It's something you can look out for if you're having to calculate a lot of x's and y components. you can always just switch the frame a little bit. Switch it, it'll make the calculation easier. We just get this F and T instead of having to do a massive ass calculation. Okay, so that's 3 great examples. You've got a monster of a worksheet, which is really good. And now we've covered all those kind of simple force scenarios now. One of the concepts which we were introduced to here was the idea of connection and even tension. I'll be exploring those a little deeper. Okay, right. I briefly want to discuss here the idea of connection to really sort of cap off this forces exploration that we've been doing. Connection is a topic which is introduced frequently within mechanics, physics, yes, even mathematics. Connection between things. And I want to take it out of the context there and say that connection is probably the most important thing as a human being that we need. Connection to nature, connection to others, connection to ourselves. There's many things that are connected and many profound connections occurring all around you. I mean, there's things like quantum entanglement, which is, if you're interested, you can look up, where particles seem to have entanglement over vast distances, connected in sort of weird ways which we don't really understand, but they are. And there's, I would say, most likely, most definitely actually, there's many connections that we can't see. I mean, even if we just take this idea of force and how things are connected through forces, they're repulsed, repelled, or drawn to each other. You can't actually see that force. You can see the objects moving towards each other, but there's this weird mysterious force which is bringing them together. Gravity, another example. And I would say there's also deeper connections going on, such as hate, love. There's connected forces between people and in nature. They're all around you, and there's probably even connective forces that we're not even seeing, haven't even discovered. Will in the future, and when these connections are found, they are usually transformative for humankind. So just want to kind of open you up to, when you walk around, I just want you to sort of observe how you yourself are being pulled and repulsed, and sort of you have there's sort of like a connective field around you between objects, emotions, and all these things. Yeah, just really want to introduce that. I'm not going to go too deep into this one. I just wanted to bring it up. Connection is an extremely powerful thing and a prominent thing in your life. It's not just between physical objects. It's within you, baby. Yeah, that's it. If you found this video useful, please subscribe, please like, and thank you to all the people who have purchased my courses. That's about it. Peace and love, baby.